Hello. So we're recording. Hello, YouTube. So yeah, right. For those of you who are sort of just watching this for the first time on YouTube, just want to let you know that we will tentatively try to have an exam on Wednesday, April 22nd. That's in 16 days. And the idea is that you will do it right. You'll see the questions on the screen, either through Canvas or email or something, and you will do the questions on paper and take pictures of them and submit them by Canvas, uh, uh, just as you would submit a homework. And then I'll sort of grade them inside Canvas. I've actually discovered one of the strange things I have now discovered is that it's actually easier to grade stuff in Canvas, inside that Canvas speed grader, than it is to sort of do it on paper. No one is happy. Actually, no one is happier to hear about that than my wife, who is for decades wished that I would stop leaving these huge stacks of paper around the house, and so that may actually happen. So I don't know. This is not a great way to learn that Canvas grading works well, but needs must, as the devil drives. And so actually, probably even after this is over, I will probably keep grading homework on Canvas. Anyway, so are there any last questions? Oops, so there is a question on chat. Oh, Ishan. So what if we can't guarantee a quiet working area for the midterm? On the mid, I mean, so there would be just like sort of chaos around you in the house. Okay, send that to me in an email. Yeah. I guess we'll do the best we can. One thing that I mean, I don't know. Can you lock yourself in the bathroom for 75 minutes? Honestly, that's how I had to. Not to get too personal here, but that's actually a place I've done a lot of grading. Is in the bathroom when I'm up at 5 in the morning, and one thing about this the pandemic is that I don't have as long a commute anymore. But it used to be I would get up at 5 in the morning and want to do something, and I just lock myself in the bathroom. Or not lock myself, but I'd go into the bathroom and shut the door, and then I could do my thing, and it's very quiet. So there's my YouTube recorded overshare for the day. So yeah, inside your bathroom is actually a pretty reasonable place to do this, or not reasonable, but it's less unreasonable than other places. Okay, so yeah, so let me know if you want to talk more about your situation in detail. I'd be happy to talk to you just by phone or by one of these Zoom meetings. Yeah, I think by phone would probably just let me know. Just drop me an email, and I'll arrange a time to talk by phone. I guess is probably the best way to do that, about your personal situation and how we can sort of make accommodations for that if possible. Okay. Are there any questions so far? Okay, so no questions so far, but I hope we can sort of have something resembling a normal classroom exam without increasing everybody's stress levels too much, or at least not increasing it much more beyond the place where they normally are increased. Not much more than usual anyway. Okay, and so I'll have more. We'll do an exercise about that on Wednesday, and I'll have more details about that once we see how that goes. Okay, let's do some math. So where did we leave off? So we left off with the idea of a principal ideal domain, and with this very important definition, to say that a ring R is a principal ideal domain, or PID, means that R is an integral domain, that is, it has a zero factor property, so nothing too silly happens in that ring, and that every ideal of R is principal, which means, if you don't remember the definition of principal ideal, so this over here that's the definition of principal ideal. That's an ideal. So to say that an ideal is principal means that it is the set of all capital R multiples of some particular element A. Anyway, so the second condition says that if you have an ideal, it has to be all multiples of some particular A. And so, the result, the important theorem, whose somewhat less important proof we discussed, but it's good to discuss because I have you sort of duplicate that on the homework. The important theorem that we talked about last time is that if R is either the integers or the ring of polynomials with coefficients in a field, then R is a principal ideal domain, which means that. So again, to repeat, to say that R is a principal ideal domain, so either for if R is either the integers or polynomials with coefficients in some field, that means any ideal of R is the set of all multiples, all R multiples of some fixed element of R. So that's and again, besides that, there's like one homework problem about it. But besides that, the proof of this is not so important. The fact, but what I really want you to retain is the idea that that these things are principal ideal. That both the integers and any ring of polynomials with coefficients with field coefficients in field F. In either of those rings, any ideal is the set of all R multiples of some fixed element of R. Okay, so here's a particular case, sort of consequence of that, or a definition and sort of consequence of that. So let F be a field, and let I be an ideal of F bracket X. To say that d of x is the minimal polynomial of capital I means that I is generated by d of x is in other words. So again, let me remind you again of the definition of principal ideal and the ideal generated by a single element. So this means that, again, so I is the set of all polynomial multiples of d of x in this particular case. So for when you have a principal ideal in the integers, it's the set of all integer multiples of some fixed A, and here this is this capitalized the set of all polynomial multiples of some fixed D. And so that D, what exists? So that element D of x exists because F bracket X is a principal ideal domain, and it turns out in D of X, so many things left out here. D of X turns out to be unique up to associates. That's not so important that but that's a sort of a thing that we've encountered before. So in practice, we will actually encounter ideals in practice that we have to try to understand, believe it or not, and use to make money of all things. So if you have an ideal in a ring of polynomials, how do you compute its minimal polynomial? Well, the answer is it depends on how that ideal has been specified. But here's one particular case. So let F be a field, and consider the ideal I, which is generated by two polynomials a of x and b of x. So so what does that mean? Let me remind you what this notation means. This means that by definition, so I kind of lost my touch in making these boxes get bigger. Okay, there we go. So I is the set of all polynomial linear combinations of A and B, things that look like R of X, A of X plus S of X, B of X. The set of all such things. Right. So yeah. So suppose you have so in the homework, and I think in the homework you're going to show that that's an ideal if you look at all polynomial linear combinations of two fixed polynomials A and B, then that's an ideal of the ring F bracket X. And so so the theorem, the theorem, the principal ideal. Oops. Oh no, what was that? All right, there we go. So the principal ideal theorem that we sort of mentioned up here, that F bracket X is a PID, says that there must exist some D such that this other ideal is actually just all the multiples of D, and so what is that D? The minimum. Well, it turns out the minimum polynomial is actually, guess what? The GCD of A of X and B of X, and it's computed by. Let's see, it's always a rough reentry coming back from spring break. Let's see if so. Does anyone remember what do you use to compute the GCD of two polynomials? Type it in the chat. Yes, EA, computed by, yep, the Euclidean algorithm. It's always the Euclidean algorithm. Right. Yeah, the Euclidean algorithm is like the answer. It's like one of the two algorithms that we'll learn, really, that you'll learn in this course, because, well, I mean, you learn other algorithms, but they all sort of boil down to, like, well, the Euclidean algorithm. I guess we also briefly looked at row reduction, but not really. I mean, it's Euclidean algorithm. Anyway, yeah, the Euclidean algorithm is somehow the answer to everything. Okay, so so suppose what we want to show that the set. Ooh, right. And this actually came up in the homework, and I had a nice conversation with somebody about this, like, over email. So let me remind you, or maybe tell you. Let me actually take a survey, and there's no shame in saying no to this. So can you just type in the chat? Do you remember in Math 42 talking about how to show that, or prove / show that two sets are equal? So yes or no? Do you remember talking about discussing in Math 42 how to prove that two sets are equal, or some similar? Okay, so it seems. Yeah. Okay. Yes. Yeah, so and those of you, somebody asking, yes, it's exactly, if there's, so to show that to prove two sets A and B are equal. It's okay if you don't remember it, because I'm telling you now. Prove that A is a subset of B and vice versa, and B is a subset of A. Yeah, and so yeah, Ishan, that's exactly right. The way to prove that two sets are equal, and remember these are two sets here. The ideal generated by D of X and the ideals generated by A and B. Yeah, so to prove that they're equal, you prove that one is each of the subset of the other. So that's the first note, and the second note is that to prove that A is a subset of B, you consider an arbitrary element of A and prove that it must be also an element of B. There's a reminder of how to prove this, or by reminder, it might actually be I might actually just be telling you that. That's okay. Let's see. And I think, okay. So and I think I need another page here. So let me stick in another page here. Yeah, by the end of today, I will be all fresh. I have to say, like, when I did my 9 o'clock, I totally did not remember how to do all these things, and now I'm sort of getting back into it a little bit. Yeah, it's always a little rusty. I always feel a little rusty coming back from spring break, even a sort of weird quote spring break unquote like we just had. All right, so to show that the ideal generated by A and B is a subset of the ideal generated by D. We assume, remember, capital A means assume, f of x is in the ideal generated by A and B. And eventually, somewhere down here, we want to conclude that f of x is in the ideal generated by d of x. And remember, the ideal generated, oops, that wasn't what I wanted to do. The ideal generated by d of x is the set of all polynomial multiples of d of x. So here, and this other set here is, comma, the set of all f bracket x linear combinations of a of x, b of x. So what happens? I think I better switch to pen actually. So the initial assumption is that f of x is equal to r of x, a of x, oops, a of x plus s of x, b of x, where r and s are polynomials. So that's where we start out. And what we wanted to conclude is that f of x is equal to, I guess, rs p of x, d of x for some p, some polynomial p. Okay, so so what we want to do is we start off by assuming that f of x is some polynomial times a plus another polynomial times b. That's what it means. That's what it means to be an element of the ideal generated by a and b. And we want to end up by saying that f of x is some polynomial times d, for some some polynomial times d. So do those start and ending? Are there any questions about those start and ending points? Type them in the chat. Okay, so so moving on. The point is that D is the GCD of A and B. So it divides both of those. So that means that I think I can actually just type this. That's a lot easier to read. Yeah. So that means that G is equal to D is equal to the GCD of A and B, which means that A of x is equal to, I need more letters here. G of x, D of x, and B of x equals H of x, D of x for some G of x, H of x in f bracket x. So for some polynomials G and H, which means that if we combine all that stuff together, we see that f of x is equal to r of x times a of x, which is g of x, times d of x, plus s of x and S of x times H of x times D of x is equal to, if I collect all that stuff in the front, R times G plus, plus S times H, all that stuff times D of x. Which means that, yeah, and so this is, I don't want to do that. So that's your polynomial P. And so, so yeah, so we see that f of x is some polynomial times d of x, and we're done. Period. So that's one direction. So everybody good so far? Any questions so far? Okay, so let's do the other side. So remember, yeah, so we just said that to prove that two subsets are two sets are equal, you prove that the first is a subset of the second is a subset of the first. So now we want to show that d of x is that the ideal generated by d of x is a subset of the ideals generated by a of x and b of x. And so now we make exactly, I'm going to do something cheesy here. I'm going to cut and paste. So now we reverse exactly. It's actually cut and paste with a reason here. Is this going to work? See, there's some advantages to doing this nutty thing here. So so I'm gonna, that was the assumption of the previous one, and this is going to be that this is the conclusion of the previous one. There we go. And so now to prove the converse, to prove that d of x is the ideal generated by d is a subset of the ideal generated by a and b. Well, we switch the assumption of the conclusion. So now we first assume that f is in D, the set of all f of bracket x multiples of d bracket x, and we want to conclude that f is little f of x is a big f of x, f bracket x, linear combination of a and b, and so we assume here, so f of x equals I think I said q of x times d of x. Still not quite gotten the hang of, oh, whatever. All right, so yeah, hang on. So f equals qd for some polynomial q of x in f bracket x. So that's what that assumption means, and the conclusion, the way that we will be able to reach the conclusion that we want to reach, is that we will have to we'll have to show that f of x is equal to r times a plus s times b, sum r of x and s of x, f bracket x. So it's not distracting, but I'm picking up a little background noise. So you might want to mute yourself, just so nothing embarrassing gets preserved on YouTube for posterity. Oh, we have questions in the chat. Oh, yes. Can you show us the whole page? Sure. Okay. Let me go to whole page. Fan, is that better? You can see the whole page. The type's a little small now, but can you see the whole page a little better? Does that help? Oh, the whole previous page. Yes. There. All right, so that makes sense. Yeah. So yeah. So again, yeah, to show that this is how you show that two sets are equal, and this is how you prove that one set is subset of the other. And then yeah, so we start out in the one side of the proof. We assumed that we had a linear combination of A and B, and we ended up concluding that that linear combination of A and B is a multiple of D. And now we're assuming that we have a multiple of D, and we eventually want to conclude that we have a linear combination of A and B. So, Fan, does that help? Okay, great. All right, so now we're assuming that f is q times d for some polynomial q, but from Euclidean rewriting, we know that letters here, yeah, that d of x is a linear combination of a and b. Is equal to g of x, a of x, plus h of x, b of x, for some g and polynomials g of x and h of x in f bracket x. This was like all the stuff about Bézout for polynomials, Bézout's formula, and Euclidean algorithm, Euclidean rewriting polynomials. Yeah, so if you remember, if you were wondering back then, why on earth are we doing the Euclidean rewriting? This is actually one reason why. We'll see actually a better reason. I think starting on either on Wednesday or on Monday. At least starting on Wednesday, and then maybe also on Monday. So yeah, so we know from before that that's true. So so f of x is equal to q of x times that. The q of x times this other term, ga plus hb, is equal to qd qg a of x plus qh b of x. So that means, so that's what we want. F of x is now equal to some polynomial times a plus some other polynomial times b. And so we're done. So so we good? So is everybody good with that? Or are there questions? So you please say either yes, or I'm okay with that, or ask a question in the chat. No questions, but not a lot of yeses either. Yeah, so I think, so what is so I'm gonna guess that this seems mysterious still to some folks. So I think the thing to do, so if this all seemed mysterious, you're like, what just happened there? What is even going on? Here's what I suggest you do. So if the above seems mysterious, go do the problem from 7.1. I think this is on, I forget what problem set this is on, but go do there's a problem assigned from 7.1 where you prove that the ideal generated by two elements A and B, prove that for a ring R and A and B in R, the set A comma B, which is the set of all RA plus SB, where R and S are in R. Prove that is an ideal of R. So I think if this, I mean, you don't need to do too much, know too much about this. But I thought it'd sort of be useful to sort of look at to look at some of the theory of this. But if the above seems mysterious, I think a good review is to go back and look at the there's a problem assigned in the homework. I think it was problem set 7. Where you have to prove that if you have a ring, capital R, and you have two elements A and B in capital R, then that set of all R so this is the set of R linear combinations of A and B. That prove that that's an ideal of R, and so and once you do that, that'll sort of shed more light on the definitions going on here. And once you sort of know the definitions, the only real content is just these. It's really just this line here about Euclidean rewriting in Bézut's formula. Okay, so I think so everybody who didn't say yes or ask a question, well, I guess is probably surrendering for the moment. Please, please stop. All right, so oh, hi, Matt. Since we're using Bézut's, we're finding the inverses of A and B and F bracket X. Not yet. So this is just rewriting. So the only way we're using. We will eventually do something like that. You are perceptive there, but here, what we're doing. Oh yeah, that's right. That's right. We did something. We did that with a quotient ring, with the quotient rings. So this is just we're not exactly finding an inverse because there's no modulus. Remember, if we had an M here, then that'd be finding an inverse. But here we're just rewriting. Yeah. So I think it's probably correct to say here this is really just literally rewriting. So, I forgot that happens. Just rewriting. Yeah, thank you for that, Nat. Thank you for that question. Yeah, not an inverse, which is the thing we saw. That's right, the thing we saw last time, that which is actually the main use of Euclidean polynomial Euclidean rewriting, is finding those inverses, as we'll see soon enough. Okay, any other questions? Okay, so beyond that, I just want to mention one pure theory thing. So just really in passing. So if you're interested in theory, yeah. So what do I even truly show that you would be interested in theory? Which is not. This is not something I did when I studied this stuff. But you might be wondering. You might have wondered at some point, like, how do I really know that unique factorization works? I mean, okay, so you were taught unique factorization in the integers works. I know this because in 4th grade, because I know this because my daughter is learning that right now. And at some point in high school, probably somebody assured you that, oh yeah, you can factor polynomials just like you factor integers. But if you ever wonder like how to prove that, in fact, even prove it in the integers. So proving if you want to prove that follows from the result that if you have a principal ideal domain, that then unique factorization holds. That's outside the scope of this class, but if you're interested, that's really the key point in every proof of unique factorization in either the integers or the ring of polynomials that I have seen. Anyway, so just so you know that that's the name of that tune. Okay, so oh right, so we're going to move on. So any quick questions before we move on from theory to theory? This is going to be some serious theory coming up here, which, believe it or not, is I was sort of preparing this upcoming session. I said, oh, I can skip. Wow, this next section is really theory-ish. It's pretty abstract. So let's skip it. And then I realized, oh no, that's right. It's actually something we're going to use to make money. Believe it or not, this next thing, which I mean, I don't think it'll seem so complicated necessarily. But this next thing is that I'm sure it will seem like, how on earth would you ever use this to make money? But you do. We will. So before we move on to sort of someplace where the air is pretty thin, any questions about this so far? About principal ideal domains, or this or how to find the minimal polynomial of some ideal of polynomials. Okay, so and now, as they say on Monty Python, and now for something, the old Monty Python segue, and now for something completely different. Hey, I can, since this is going on YouTube, I can record my terrible British accent for posterity. And now for something completely different. Yes, there we go. Yes, I did spend my misspent youth was in fact misspent watching a lot of Monty Python. I grew up in Maine. There's nothing else to do. Okay, so this is going to be so our next section is about homomorphisms. Well, it's not completely different in that the last thing was theory-ish, and this is really theory-ish. It'll sort of start from nowhere, but it's okay. So homomorphisms are pretty homomorphisms. I say that I should say that more clearly for YouTube. Homomorphisms are pretty abstract. However, they turn out to be surprisingly important for building better codes. We're going to look at one particular method of building better codes with larger minimum distances. It's called they're going to be called BCH codes, and it turns out that one important ingredient in building a good BCH code is actually it's what's called a field automorphism. So we'll get to that. That's sort of the goal. That's actually our only reason for introducing this. I mean, I guess I like this. I'll be honest. I quite enjoy this kind of abstract bit of homomorphisms, but the money-making application will actually be building better codes. So with that in mind, let's get totally abstract. So let R and R prime be rings. To say that, so if we have a function phi, whose right, you can tell that it's got an abstract here because we're using we're calling out the Greek letters here. Quote phi. So that symbol there is pronounced phi. And it can be written. It can be written either like this or like this. I guess I prefer this one, as you can see, because this one looks too much like the empty set to me. But okay, I will accept either. So to say that function phi from the ring capital R to the ring capital R prime is a homomorphism. It means that for all little r and little s in capital R, phi of r plus s is equal to phi of r plus phi of s, and phi of r times s is equal to phi of r times phi of s. In other words, a homomorphism is a function between rings that preserves addition and multiplication. So if you do sort of the theorem proving version of this class, the one that really emphasizes theorem proving and almost not at all very much less applications, this is the idea of a homomorphism is one of the fundamental ideas of the course. For us, and we will spend some time talking about it today. But again, this is towards making. There's a point here where you sort of make money with it. I know, right? For example, let me take the idea. So one example of a homomorphism that you have seen is quotient rings. So remember, let R be a ring, and let I be an ideal of R. So remember, if we're going to define a function whose inputs are in capital R and whose outputs are in capital R mod I, remember capital R mod I is as a set of all additive sets of I in R. So let me remind you, that's how you define the quotient ring R mod I. Well, if I define a function whose inputs are in R and whose outputs in R mod I by sending if phi of R sends R to the sort of corresponding coset R plus I, well, then it turns out that that's a homomorphism, because the two conditions of the definition of homomorphism, become, well, actually I should sort of say what this is. So this on the left-hand side is phi of R plus S. And on the right-hand side, we have phi of R plus phi of S. And we see that the two conditions in the definition of homomorphism, one is phi of R plus S equals phi of R plus phi of S, and the other is that phi of R times S is equal to phi of R times phi of S. Well, those become the equations R plus S plus I equals R plus I plus S plus I, and RS plus I is equal to R plus I times S plus I. Well, but those two things are exactly the definition of addition and multiplication in R mod I. So if you remember these are exactly the definition of addition and multiplication. Oops. Right. Addition and multiplication in R mod I. And so they hold by definition. And it's like the least satisfying thing to say, but it is true. So what's really going on here is that whoever, I guess I know what the clever person that is actually a great mathematician named Emmy Noether is the mother of abstract nonsense in math, and a wonderful thing that she invented here. Anyway, these are exactly the definition of the quotient ring R mod I. And in fact, that definition you can think of as really being chosen in order to make this function phi a homomorphism. And we call that function phi the canonical homomorphism from R to R mod I. So there's one example of a homomorphism that you have already seen. And that would have been more spectacular if I'd gone to the whole page view like I wanted to. Okay, there we go. So any questions so far about this, about the definition of homomorphism or this example of homomorphism coming from quotient rings? Okay, so that's one example of a homomorphism. I think I have another example coming up here. Yep. So here's another homomorphism. Okay, so here's another. So let F be a field. You can just think of F as being like the rationals of the real, something familiar if you like. But also, I guess I should say, when I think of being F, it could be the rationals or the reals, or actually we're going to use think of the complex numbers in a minute, or you can think of Z mod P. That's a good one. And those are really all the examples of fields that we ever deal with in this class. So let capital F be a field, and let alpha be an element, one fixed element of capital F. So I'm going to define a function that takes as input a polynomial. So so let me remind you what this notation up here means. So this means inputs are polynomials, outputs are field elements. Yeah, so that's so this is a function whose inputs are polynomials, so outputs are elements of F, and it's defined by the formula phi of f of x equals f of alpha. So to apply phi to f of x, you just plug in alpha for x. So it turns out that phi is a homomorphism. So what does that mean? So on the one hand, if you look at so for do I mean IE or EG? Anybody seen the movie Get Shorty? Great movie. And there's a lengthy description of this discussion of IE versus EG, followed by somebody getting beat up. That's entertainment. Anyway, so for example, if you look at the definition of homomorphism, one of the things that shows up in the definition of homomorphism is that you want to compare phi of, let's say, f of x plus g of x versus phi of f of x plus phi of g of x. Let me do the second one first. The second, because it's a little easier to describe what's going on. So if you look at phi of f of x, that is by it says so right up here. Look, there it is, right up there. It says by definition that by definition is f of alpha, and phi of g of x is g of alpha. And let me be kind of precise. Try to be precise about what's happening over here. So when you compute, when you look at this expression here, what you're really doing is you substitute alpha first, then add the results. Now, on the other hand, when we look at, I'm going to use a sort of strange notation, a temporary kind of odd notation that you may have seen. And I know you saw it in like calculus or something, and just for like one day and then never spoke of it again. So I'm gonna write in the result of adding the polynomials f of x plus g of x as parens f plus g of x. So this is, so what is this? Is the result of adding two polynomials. And so on the other side of the definition of homomorphism, so you get get the result of adding two polynomials first, and then plugging in that constant alpha. And so that first property of homomorphisms says these are equal. So yeah, so if phi is indeed a homomorphism, then these two sides, the thing you get by adding polynomials first and then plugging in, then plug in alpha. So in order for phi to be homomorphism, you need that if you take two polynomials, if you add them as polynomials first and then plug in alpha, you get the same result if you plug in alpha first and then add the results. So it doesn't. So the point is that phi being a homomorphism and similarly for multiplication. So yeah, so phi being a homomorphism is equivalent to saying that it doesn't matter if you substitute before you add or multiply polynomials or afterwards. And I have to say that there's no reason on earth you ever would have thought this could possibly not happen, because the notation for polynomials is chosen to make this look like, well, of course it's going to happen, because we made f of x and g of x look like functions, whereas though if you sort of the thing is, they're not actually functions. If you sort of dig in into the details, they're not actually functions, and so it's a little bit misleading. But at least that does make this sort of well, I don't know, for better or worse, the notation of writing out polynomials as f of x as functions makes this look obvious, or at least natural, when it perhaps isn't if you think about it hard enough. Anyway, so the point is, but it does work. it does work, and because phi is in fact a homomorphism. All right, so this substitution homomorphism is another example of a homomorphism that you've actually implicitly used at one point, in a very subtle way. Yeah. Okay, so there's two examples. There's the example of quotient rings, of a homomorphism coming from quotient rings, and a homomorphism coming from substitution. Any questions so far? Okay, so I hope at least that gives some idea of what the definition looks like and what it might mean in at least a couple circumstances. So let's move on to some initial properties of homomorphisms. So for example, let R and R prime be rings whose additive identity elements are 0 and 0 prime, and let phi be a homomorphism from R to R prime. Then, oops, I have this thing saying proof of B, so I guess I better write an A and a B here. So this is A, B. I'll just do it in pen. So this is A, and this is B. There we go. So I want to prove. Then any homomorphism has to send the additive identity element of the input to the additive identity output of any homomorphism must send the additive identity of the domain to the additive identity of the codomain. So that is phi of 0 equals 0 prime. And for every element of the domain, phi of negatives, phi of negative R is equal to negative phi of R. So I guess in terms of slogans, you could summarize these things by saying that, oops, morphisms preserve the 0 element. This says that homomorphisms send negatives to negatives. So let me prove part B. So how do we go about this sort of proof? We want to assume that little r is in big R, and that phi is a homomorphism, and the other stuff that we assumed before, and eventually we want to conclude that phi of negative R is equal to the negative of phi of R. Well, it's it's probably not clear how to, so the following thing I'm about to do takes some work, but here's one way to do this. If you look at phi, then it is the case that phi of R plus phi of negative R is equal to phi of R minus R. So that's the definition of homomorphism. All right, I guess if I want to be a little fussy, let me be a little bit fussy about that. Phi plus parens negative R. So that was exactly the I guess there's not quite enough room here, so I would say these green arrows will represent the definition of homomorphism. All right, go back to pen, red pen. All right, so this is equal to phi of R plus minus R, which is equal to phi of 0, which we in part A shows that we would have shown, let's assume that we already did part A, and we would have shown is equal to 0 prime. And so, yeah, so phi of r plus phi of minus r is equal to 0 prime. So I want to subtract phi of r from both sides. And so we get that phi of minus r is equal to 0 prime minus phi of r, which is the same thing as saying minus phi of r. And so, yes, indeed, phi of minus r is equal to minus phi of r. All right, so that was a little cramped in. I didn't plan that spacing out quite okay. So I'll give myself a half smile for that. You know, minus several points for typography. But does that make sense so far? Does that kind of make sense? Please say yes or ask a question in the comments. Okay, right, and so yeah, so here's a homework problem for you guys. So suppose we have 3 rings, R prime, and R double prime, and let phi be a homomorphism from R to R prime, and rho be a homomorphism, row your boat. I got dad jokes. So this thing is pronounced row. Dad jokes. There we go. So yeah, this is phi over here, and this is rho. Rho is a homomorphism from R prime to R double prime. Suppose those are both homomorphisms. And so the only way you can compose these two things is phi compose. Rho compose phi. Is rho compose phi. Remember, so rho is like your outside function, phi is your inside function, and that has to have domain capital R and codomain R double prime. And so then it is a fact that that'll be on your homework that rho compose phi is a homomorphism. And so that I think the best way to get the hang of the definition of homomorphism is to do a problem like this. So and this will be on problem set 9, I guess. Gosh, we've gotten a bit over our skis here, a bit ahead of the homework. So maybe we'll slow down a bit. Yeah, we should probably, because yeah, there's no point in rushing this too much. So let me. Obviously, this is like something that's due next week. So maybe we've gotten a little bit too far ahead of the homework. But okay, are there any questions about the definition of homomorphism, or are we? Should I proceed? Okay, so let me go to I want to talk about I want to talk about isomorphisms. That's right, and then I want to talk about automorphisms. And automorphism, I think that'll be the end of today. Automorphisms. So an isomorphism is a bijective, right? Homomorphism and now isomorphism. So an isomorphism is a bijective. Remember, I hope you all saw bijections in Math 42. There are one or something, one-to-one and onto functions. So an isomorphism is a homomorphism that is also one-to-one and onto, also a bijection. So to say that rings R and R prime are isomorphic means that there exists some unstated isomorphism phi from R to R prime. So, and why is that important? Well, the point is that if you have an isomorphism phi from R to R prime, then because phi is a bijective correspondence, because and preserves the ring operations, because phi is a bijection and preserves the ring operations, that means that R and R prime are really the same thing with different names for their elements. And conversely, if R and R prime have different algebraic properties, they can't be isomorphic. So I guess the point of this is that Yeah, what do I really mean by this? What I really mean is, I have to get better making this, expanding this box. There we go. If you take Z mod 3, which remember has 0, 1, and 2 in it, and rename the elements Mo, Larry, and Curly. Wise guy, huh? Stooges? No, I wonder if I'll get a copyright violation for quoting the Three Stooges. Oh well. Anyway, so if I take the Zmod 3, which has the elements 0, 1, and 2, and I rename those elements Mo and Larry and Curly, but preserve all of the algebraic operations. For example, I guess if Larry is 1, then Larry plus Curly will be equal to 0. Then you haven't really made a new ring. You've just given different names. You're just using different names for the old ring. So we would say that Mo, Larry, Curly is isomorphic to Zmod 3. Yeah, so isomorphic rings are rings that where you should really have the same algebraic operations going on, but you just use different names for some strange reason. And so we say that. So there's an example. So that's the point of an isomorphism. In some ways, it's easier to think about than a homomorphism, is because you're really just isomorphism is really just a way of saying that you're renaming things. Oops. So here's some properties preserved by isomorphisms, except that I seem to have had some sort of typo here. If two rings R and R prime that are isomorphic, then R and R prime must have the same number of elements if they're finite, because there's some bijection between them. They have the same number of units. There's a bijection between the units of R and the units of R prime, the things that have inverses. Capital R is an integral domain if and only if R prime is an integral domain. These are kind of all a bunch of the sort of abstract things we've defined in ring theory. Capital R is a field if and only if capital R prime is a field, and capital R is a principal ideal domain exactly when R prime is a principal ideal domain. In fact, if I'm sort of being a little bit laid back about definitions, I would just say that R and R prime are the same ring. So really up here, Z mod 3 and Mo, Larry, Curly are the same ring. They're just using different names. Yes, okay. So this is a good place to stop. This is the last thing we'll do today. So let R be right. So these so the question is, let R be F2 bracket X mod X squared plus 1. Let R2 be F2 bracket X mod X squared plus X plus 1. And let R3 be Z mod 4. So I first want to note that actually, let me do this in pen first. Since both R1 and R2 have the form, well, we're modding out by, so remember, we're modding out by polynomial degree 2, and so we can write the elements of, oh yeah, and let's call this F2 adjoin alpha, and let's call this F2 adjoin beta. And so, erase all this stuff. So since R1 is equal to, has the elements 0, 1, alpha, alpha plus 1, those are all the elements of degree, polynomials of degree at most 1 in alpha, and it's most 1 because we're modding out by polynomial of degree 2. And R2 has the elements 0, 1, beta, beta plus 1. And R3, Z mod 4, that has the elements 0, 1, 2, 3. I first want to note that these all have the same, that all three rings have the same number of elements. So they could be isomorphic so far as we've seen. However, I want to point out, on the other hand, that R1 is however, so it's very much not obvious that as it turns out that none of these three rings is isomorphic to any of the other two. So, but it turns out that these three rings are pairwise not isomorphic. In other words, i.e., all three of them are different. We show this by finding abstract properties that distinguish them. Three rings. So, for example, so here's, I think that this is where we will finish because we're running out of time. So if you look at in R1, so in R1, we know that alpha squared plus 1 equals 0. So this is, yeah, that's right. This is the thing we spent some time on last time, because because alpha is, we're joining this root alpha of x squared plus 1. That means that alpha plus 1 equals 0. So if we look at alpha plus 1 quantity squared, that's equal to alpha squared plus 2 alpha plus 1, which is equal to alpha squared plus 1, because, and let me remind you that because we start off with in the ring of polynomials with coefficients mod 2, and the coefficients are still mod 2. So this is still, everything's working mod 2. And so that 2 alpha goes away, and so we get alpha plus 1 squared is alpha squared plus 1, which is equal to 0. Mod alpha squared plus 1. And so R1 has 0 divisors. And in R3, 2 times 2 is 4, which is 0, because this is the ring Z mod 4. And but on the other hand, turns out, yeah, this we saw last time. But on the other hand, x squared plus x plus 1 is irreducible over F2. So R2, which is, remember, F2 x mod x squared plus x plus 1 is a field. And so the conclusion is that, should I just write it over here? So I should use this and do this in a different color. I'll do this in orange just for kicks. So in orange, so R2 is not isomorphic to either R1 or R3. And you can actually also show this is a good place to stop here. And so you can also show that R1 and R3 are not isomorphic. And so I'll leave that to you as to y'all as an exercise. Oh, phew. Okay, so I guess next time we'll start with automorphisms, which are really the immediate application of what's going on. So thank you very much. Welcome back from your spring break, such as it was. Thank you very much for your attention, your time. You could have been any place on the internet, but and let me answer your chat questions. Right. So Jake asks. So basically the same. Yes, the same set of. So when two rings are isomorphic, they're basically the same set of numbers described two different ways. Exactly. 0, 1, 2, and Larry, Moe, and Curly. And what we're showing here is that there's no way of like sort of renumbering, say, sort of matching up R1 and R2 in a way that preserves the algebraic operations, because R1 has zero divisors. And oh yeah, I didn't actually say what was so special about finding this. So so R1 and R3 have zero divisors. That was the main point of that. Sorry. Yeah, so R1 and R3 have zero divisors, but R2 is a field, and so it doesn't. And so R2 is not isomorphic to either R1 or R3. And Nat asks, should you highlight the difference between homomorphisms and isomorphisms? What happens? So here, let me go back and look at one example, which is, quotient rings. So remember, when you take a quotient ring, one example of what's going on here, an example of the example, so to speak. So example of example. We have phi going from the integers to z mod 7, and that's an answer to Nat's question, like, can you highlight the differences between homomorphisms and isomorphisms? Because that's an example. Phi squishes lots of stuff together. Say 0, 7, 14, 21, 28, and so on. So that homomorphism is not an isomorphism, because it sends lots of stuff to the single element 0 of z mod 7. Okay, we're 3 minutes over. I apologize for running over. We went a little bit deep today. It's for the first day from after spring break, and we went over 3 minutes. So thank you very much for your time. Sorry to run over. And so remember, see if you can be prepared to be in a place to turn your camera on Wednesday if you can. And if that's problematic, let me know. Send me an email, and I'll call you on the phone. This phone thing, I know this is offensive to people younger than the age of 40, but I'll call you on this phone thing, and we'll have a short conversation about what we can do about that. Anyway, thank you very much for your time, and take care, stay safe, keep your head up, and I'll talk to you on Wednesday.